Okay, today is lesson 8.1. It's day 2 about logs and exponentials. All right, what you see before you is a couple of examples of graphs or sketches that we're supposed to do of exponentials. One's got a base 2, the other one's got a base e. Ooh, what's that mean? Well, if you know what e is, it's really easy. It's just like the same thing except it's got a base of 2 point what? 2.718. Good. All right, so this has a base 2. This has a base 2.718. So this one's got a little bit bigger base. What do exponentials look like in the first place? All right, what I'm graphing right now is the parent exponential. The exponential graph generally looks like that. And there's an asymptote line running along at 0. Because if you take 2 and put it to a power, you can never make that 2 turn into 0. Think about it. 2 to the first power gives you 2. You can make it get small, but you can't make it disappear by putting it to a power. You definitely can't put something to a power and make it get negative. So this will never cross that dotted line. All right. I won't touch the dotted line, it won't hit 0, and I won't cross the dotted line and go negative. How about this spot? All logs, unless they have been shifted, will go through that spot because it's 0, 1, and what does that mean? Yeah, you're taking something and putting it to the 0 power. If x is 0, then I'm sticking in x is 0. Then I'm getting 2 to the 0, which is equal to 1. But, like I said, if it hasn't been shifted, it'll go through this. This one, this comes out to 1 after I put in a 0 for x. 2 to the 0 becomes 1. And then I add 1 to it, it becomes 2. So actually, this graph is the parent graph. And do you get how I have to do, because that plus 1, I have to shift it up 1? The parent, but shift it up 1. Does that make sense to you? Okay. Here's a parent graph, except shifted down 1. But wait, you say, that's not exactly the same. No, it's not exactly the same. But what did I say? I would always go through on the y-axis there. 1. It always hits at 1. Are you making this graph? Because it doesn't look like it. Then I'm going to take the whole thing and move it where? Down 1. So actually, then I won't go through 1 anymore. I'll be going through 0. And then the asymptote line, which was at 0, also gets shifted down. And now it's at -1. Okay, the whole thing got shifted down 1. Now, how steep is it? Well, all I know is if I compare this one to this one, the one with the bigger base is steeper. Bigger base means that it takes a sharper turn. All right. Now let's not talk anymore. Actually, I suppose we should talk about reflections real quick. This is a parent one except reflected. Everybody sketch the parent one. I hope you know what the parent one looks like here. Exponential graph. Really looks like that. How steep is it? Well, not very steep because it's only got a 2 for a base. If it had like a base 12, it would be super steep. It'd still go through that spot, but it would get like super sharp turn after that. All right, so there's the parent one, and it's been shifted. No, it hasn't been shifted. It's been flipped. Is that an inside or an outside flip? It's inside by the x, and so therefore it's horizontal on inside, and so this is a horizontal reflection. And so for some people this is easy, and for some people it's hard. That end needs to rotate around this way, and this needs to kind of swing around that way. And the final answer ends up being pretty much like that. That's the left-right flip. So known as a horizontal reflection. That's reflected both ways. I want you to draw the parent one, and then reflect it both ways. And compare it with the kid sitting next to you. Rows 1 and 2 you're going to compare. Rows 3 and 4. Rows 5 and 6. I'll pause for a second while you try that. Okay. Hopefully you started with a parent that looked like this. and then how steep it was. Well, we can make an XY chart, by the way, if you ever need to know exactly how steep to make it. It's really not that bad. Make an XY chart, and you plug in a number for X. Like if you put in 0, of course, you get 1. But after that, if you put in like 1, you got to go e to the 1, which is 2.718 to the 1, which is 2.718. So the 1 point that would be very easy to graph is if you stick in 1, you get 2.718. This is for the parent now. So maybe I should be making mine a little steeper than that for the parent. Okay. And then I have to move it left, right, or sorry, reflect it left, right. And then I have to reflect it up, down. Final answer should be something like that one. I know spatial things can be really torturous for people. How many of you got that? Raise your hand if you did. Good. It's better than average. Okay. So moving on. These are log graphs. Just a quick reminder of the log graph. The log, I like to think of a log as a tree that got blown over. You don't call it a log unless it's actually not a tree anymore. It's like cut down and on the ground. Okay, so a log graph kind of looks like this, kind of like a tree that had roots and everything in the ground, like down here, there's the roots. And then here's the top of the tree, the big, beautiful pine tree that got blown over in the wind. Just a dumb way to remember it, but you got to have something to remember what a parent log graph looks like. And just like the other one always went through 0, 1, this one always goes through 1, 0. And if you think about it, it makes sense. Because if I put a 1 in for x, do you get when you put a 1 in that spot? You have won the argument. And if you won the argument, you get what? Nothing. And it's easy for 0, and therefore 1, 0 is a point on this graph. Okay. And then do you get, there's also an asymptote on this guy that runs this way. That's the parent log graph. And from there, you just have to move it or flip it. So let's say I wanted to move a parent log graph like to the left or to the right. If I had y equals log base 3, let's say, of x, and I want to move it to the right, do you get it's very important to, let's say I want to move it right 4. If I do that, do you get how it pretty much means I should move it down 4, not right 4? How can you tell the difference? If I put it in parentheses, that means it's part of the argument, and it's in with the x, and it's on the inside, and horizontal on the inside, remember? Gentlemen, you're missing something important. So if I put it in parentheses here, it's going to go horizontal on the inside. And if I put it out here, that is going to be different. It's going to move up or down. It's vertical on the outside. High vo, remember? So that's a vertical move. That's a horizontal move. The only difference is you put parentheses around it, and you know it's in with the x. Remember that in the front, of course, is on the outside. That is clearly on the outside, like in the past. So that's a vertical move also. Okay, so there's your general log graphs, and all they're going to ask you to do for those is the same kind of deal where you know, what's this one going to do to it? Not up 3, left 3, okay? And this one? Up 2, okay? What's the difference between a log base 4 and a log base 7? Same as last time. With exponentials, it was how sharp the turn is. With this, it's also how sharp the turn is. Log base 4, the parent one, that one is going through this spot, getting closer and closer to this line here. But how sharp the turn is, if it's log 7, I just know it's sharper. Either way, they both go through the point 0 or 1, 0, but this one just moves, it's a little bit sharper turn, because that is base 7. And then this is plus 2, that means I'll move the whole thing up 2. You get how it's really hard to tell I even moved it up 2? If you see me moving it, it's not hard to tell, but this one's left 3. That's much easier to tell, because the asymptote line used to be right on 0. Now it's like over here. Okay, so that's graphing of logs. Let's go back to these properties. I'm going to give you an example of each one. Everybody get to this page, please. This is the kind where you're splitting them up. So for instance, let's say I had log of 9x. And be careful. I'm being sneaky here. Expand this all the way. Write it down on paper. It's fine to think, but you also have to write on virtual paper. I'm going to give you a few more. Expand that one to divide. Try those 4. I'll pause for a second while I give those a shot. And then compare them with the kid next to you. Okay, here's how they should have gone. That first one, I was being sneaky because if you just do this log 9 plus log x, you missed the point. Who knows what I did wrong? Yes, sir. Okay, you're right that I didn't write the base, but just because I didn't put a 10 there doesn't necessarily make it wrong. There's something else going on that is missing. Come on, nobody can see this? Yes. How about you make this 9 into 3 squared like you just said, and then do what? And then you move the 2 in front of it. A lot of you would not have gotten full credit for expanding all the way. That is expanded all the way. Okay. Would you care to adjust problem 2 quickly before I grade it? Since almost everybody did that wrong in problem 1, I'm guessing you might have missed something in problem 2. I'll give you a second to adjust that. Okay, so you should have said log 144, but not. Instead, you go log 12 squared minus log y squared, and then the y squared and the 12 squared have to be expanded further. So the 2 goes out front, and the 2 goes in here. Can anybody beat me? Yes? You're right, but it's always expand and simplify. So I don't mean to say there's 2 log y's and therefore log y plus log y. I get that that is expanded even further, but you're supposed to expand and simplify. But there's something else kind of like that that's messed up. Can't you factor the 12 and make that 12 into a 4 times 3 and then expand it again? Yes, you can. And then this is 2 log 4 plus 2 log 3. And then the 4 can turn into a 2 squared. And then the 2 can go out in front of that piece. Do you get what I'm saying? You could just keep on expanding these things until eventually you don't have any, like you can't break it down any further. In other words, the numbers are all primes. So yeah, you can expand. It gets kind of ridiculous how much you can expand. All right. Number 3 here is an example which I didn't assign to you yet, but it's just this. If you have log base 2 of 5 to the 7th, you can just move the 7 down in front like this. There we go. That is called a power rule. There's many things called the power rule in math, but in context of logs. All right, and then this one, anything where there's a 1 in the argument, if you've won the argument, you get nothing. Raise your hand if you had a 0 for that one. Okay, good. And then the last one I want to talk about is this one at the top here, which slide up. Move that down by accident. And this 27 could be made into a 3 to the 3rd. And then this and this are the same. The answer is that one. So the answer is 3. Raise your hand if you had that one right. Okay, good. Definitely the hardest part is that expanding on the logs. All right, so let's move on. Here is our homework, which is basically mostly graphing. I'll basically do the first one with you and have you do the other one. So on this one, it says 2 to the x. Do you get that generally speaking this is an exponential and therefore it goes like that, the parent one? Now, shouldn't we have at least a couple points on here to know we're not just completely faking it? Yes. Here's the first one. You know it goes through there. It has to go through there. The second one is you should make an XY chart and at least know one important point from it. So would you agree if I put in a 1 into this function right here, if I put in a 1 for the x, I should get what? Put a 1 right there, and then it's 2 to the 1, which is 2. 1 comma 2 is on my graph. So I guess I was a little bit too quick to graph that thing. It goes through that. So it's a little steeper than I thought it was. And that's just a base of 2. Okay, base of 3 would be even tighter turn than that. Base of 4 would be even tighter than that. Because, 4 to the first power would be over 1 and up 4. All right. So then that's the parent. And now I do this to it for my other trick. And that's the exact same graph. I'm just going to draw right over it. And you could do that too. Because then you can grab it with your little lasso tool and grab it and move it down 1. There, I moved it down 1. Both graphs are on the same graph. I'm good. Get out, it's just the parent, except move down 1. It's two funny things when you move them down 1, because it doesn't look exactly like I moved it down 1, but I did. Okay, your assignment is to do problem 60, which is very similar to the one we just did there. It's just got a little bit bigger base. So therefore, it's not going to look exactly the same. It's going to make a little bit tighter turn. And then it does have this in it. Joy. It's got a negative in there with the x. It's on the inside. Do you get how that is definitely not on the outside of this function? It's on the inside. And therefore, it's a horizontal. And if it's a negative, it's horizontal. It's a horizontal reflection. So this thing, which used to look like this, is going to get reflected horizontally. Generally look like that. And it also needs to move up too. All right. Let me tell you the ones you can skip and do. You should do this one, and I want to warn you about it, because people get confused by it just because of the positioning of that 8. But look at this one, please. Where should the 8 go to be normal? At the end, and should it be a -8 or a +8? +8 at the end. Do you get how that 8 and that 8 are the same, but one's just more confusing than the other? Okay, same idea in here. I want you to skip this one. These are log graphs now. So parent log is, again, like a tree being blown over in the wind, and so it goes through this point and generally looks like that. To get another point on it so that I can be a little more accurate, I'd make an XY chart and just pick the easy one, which is putting in x is 1. If I've won the argument, I get nothing. Yay! I already had that point, though. So maybe we should put in something else. How about I put in a 2? What's log base 2 of 2? If these two are the same, then the answer is the exponent on this one, which is 1. So 2 comma 1. I went through that already. Yay. Looks like I did this sketch pretty well. And now this is just the parent one, except moved. Where did it move? Left 1. Okay. Now down to this one. I want to rewrite this with you. The negative on the outside is easy to tell. It's negative and it's on the outside. So it's horizontal on the inside and vertical on the outside. So that's a vertical reflect. But this part gets all messed up if you write it that way. Do you get that that's the same thing as saying -x + 8? And a lot of you would just take that and say, oh, okay, so you want me to move it left 8 and do a reflect. I can do that, and you'd be wrong. Factor it. Can factor it, you should, remember? Everything, how does that factor? What can you factor out of both of them that would be helpful? The negative. The negative factors out, and what do I have left on the inside? X what? minus 8. Do you see how that's actually a move to the right of 8 and a reflect? Now, what really matters is the order that you do it in. But if you do this in the wrong order, it'd be much wiser to start with it, to do the problem that way, because you're going to make less mistakes. If you did it in the right order, you could actually still do it this way. It's not like that's wrong. They are equal to each other. But what you would start with, I remember we're on the inside. Things on the inside go in the opposite of normal order. So normally parentheses are first. So it's not first. And you'd start with that. You do reflect first and then you move at 8. If you did this in the right order, you'd be okay. What's normally first, multiply or add? Come on, answer the question. What's normally first, multiply or add? Multiply. And so then, since it's on the inside, I should do the opposite of that. And I should start with the add 8. So if I do it the way I circled in green, I would start with the add 8 and therefore go left 8 and then reflect it, as opposed to reflecting it and then moving right 8. They'll come to the same place. All right, that is one of the trickier things about reflecting and stuff, is that if you don't factor it on the inside, sometimes people get the order in the wrong order, and if you do it in the wrong order, reflects and moves, definitely, because it's basically multiply compared to add, you got to do it in the right order or it will be wrong. Okay, on to these problems, and these are important. They're not important enough to do this many, so we're going to cross off 74, and I'm going to do 71 with you. All right, this, in the directions you will see, it says you know how to find an inverse. Do you remember the 3-step process for finding an inverse? I'm going to give you like one of the simple ones. Y equals x minus 5. If I want the inverse to that, do you remember how, first thing is you change from f of x into y, and I already have a y. The second step was you change the x and the y around, because that's what inverses do. The input becomes the output and vice versa. So x equals y minus 5. And then the last step is you solve for y. X plus 5 equals y. That's the inverse to y equals x minus 5. That's the process of finding an inverse. You switch x and y around and you solve for y. All right, so let's do number 71. First of all, don't use f of x. Use what? Y. Next, switch them. X equals 3y minus 3 to the y plus 2, minus 4. And now I've given you all these little sayings, and I hope you know when to use them. Like if you can factor it, you should. There's no factoring to be done here. Get the clump alone. Did you use that in this situation? Yes. You're trying to get the y alone, and you have to get this clump alone. So how do I get that clump alone before I fix it? Add 4. X plus 4 equals 3 to the y plus 2. Now, I've got an x in the exponent. The whole reason that logs exist is because of this. Do you notice there is not a log in this problem yet? Remember me saying that half of the challenge in this unit is to get kids to realize that they need to rewrite it? So this needs to be rewritten. So this has to be rewritten as a log. Log. And as soon as you start writing log, you'll be forced to think about, okay, what's my base? And there's only one logical base in this problem, Mr. J. 3. Yep, log base 3. And then you got to jump to the other side of x plus 4. And notice me putting this in parentheses, because otherwise it'll look like I moved the whole thing up 4. No, the argument is x plus 4. And then you wrap back around and say equals y plus 2. And what was my point here? I was trying to solve for something. What was I trying to solve for? Y. And I'm almost done. What do I have to do? Subtract 2 and I'll have the y alone. I just did your first problem for you. I'd recommend copying it down quick before it disappears. do you get I just did the inverse of an exponential and I got a log? That's because if you haven't caught on to this yet, here's your classic exponential graph. Here's your classic log graph. They are inverses of each other across that line. Y equals x. Inverses, logs, and exponentials are inverses of each other. So when I took the inverse of this exponential, I got a log. All right. So you're doing 72 and 73 on this page. And then I'm going to skip the earthquake one because I have a fun, neato demo to do for you, but we don't have time today. I'm going to try to get those scores on the Can Lab from you today. We are doing 76, and we are also skipping 77. So let's cross off 77, only doing one word problem, number 76. It's about decibels. If you could remember nothing else about logs today, I'd like you to get that logs are a great way to scale something really big down to something really small. Because like for instance on the Richter scale, that's like the scale for earthquakes, a really small move on the Richter scale, like from a 4.2 to a 4.6, can actually be like 3 times bigger than the other earthquake. Okay, so a small move on that scale actually means way bigger move than it actually looks like. I'll teach you more about that tomorrow, but logs are a great way to scale a big, huge range down to something tiny. Do you get, it's hard to define how quiet, for instance, a fly rubbing its wings together would be. Okay, you could barely maybe hear that if you were in a super silent room. Okay, or some people say that the monks in Tibet can hear the grass growing. Anyway, some things are incredibly quiet, all the way to, how do you describe the difference between that and like a jet engine? You know, just like roaring so loud that it's almost deafening you at you know, like hearing it makes you deaf. Could there be a sound that's that loud? You heard only once because after that you're deaf. Yeah, an exploding earthquake, basically a mountain exploding. Earthquake causes a volcano to erupt, and then yeah, anyway. Krakatoa, tell me about that one. Really? They heard it from the Philippines all the way to Australia? Holy smokes. All right. Well, that's all I have for you for today.